study the fixed point multiplication and Cannon multiplication in pipelining for parallel and distributed systems. Let's see what is a fixed point multiplication. A pipeline multiplier based on the digit products can be designed using the digit product generation logic and the digit adders. So we will use here the digit product multiplication and the adders, and we will see how the multiplication and adders actually work. Let's take an example. 15 into 12 is equal to 180. We know this answer. Now we have to use the fixed point multiplication in pipelining to prove that 15 into 12 is equal to 180, and we get this answer. To start with, we say A is equal to 15 and B is equal to 12. As we are doing logical multiplication and logical addition, so we have to split this number into 2. So we split 15 into 2 bits. Its A0 is 1 and A1 as 5. And similarly, 12 is split as B0 is 1 and B1 as 2. Now this is put in a matrix format. Let's see how these bits come into the matrix format. We've put over here, as we've seen, A0 is 1, A1 is 5, B0 is 1 and B1 is 2. So this is what we have put it logically over here, and we'll see how the multiplication actually works. So we know the cell value for each matrix. This is A0, B0, A1, B0, A0, B1 and A1, B1. We will see how this multiplication actually comes into picture, as I have divided the cells into the imaginary lines which will help us to find out the logical addition. Now 1 into 1 is 1. The value is 1, but we need it in 2 bits, so it is written as 0 and 1. The next value is 5. 5 into 1, so it is written as 0 and 5. The next is 1 into 2, so the answer is 2. It's written as 0 and 2. 5 into 2 is 1 and 0. The answer is 10, so it is written as 1 and 0. The imaginary lines that were drawn, let's see how they come into picture. They come over here, that they divide my matrix into the imaginary areas where it will be now used for logical addition. Here you will see this last cell is come down over here as 0. The imaginary line which divides this matrix is now 5 plus 1 plus 2. So the answer is 8 over here, and 0 plus 1 plus 0, the answer is 1 over here. So finally, after this multiplication of fixed point multiplication, we get the answer as 180, which is the actual answer of 15 into 12 is equal to 180. This is how the fixed point multiplication in pipelining works. Now let's see what is a Cannon's multiplication algorithm. Cannon's multiplication algorithm use the computations of root P processes of the ith row such that at any given time each process is using a different block of A of ik, where A is my matrix. These blocks can be systematically rotated among the processes after every submatrix multiplication, so that every process gets a fresh A of ik after each rotation. We will see this in the example, how after each rotation we get a new value at A of ik. Cannon's algorithm shifts data along rows and columns of the processor. Now these are the few simple steps. Move data incrementally in the root P phase. Circulate each chunk of data among processors within a row and a column. Implements a ring broadcast algorithm. Now let's see how the Cannon multiplication algorithm actually works. We've considered here two matrices. I've not taken the values over here just to show the implementation of Cannon multiplication. I've written the rows and the columns in both the matrix, and let's see how my Cannon multiplication works. So here the first step is skew the matrix, shift each row I by I column to the left using sends and receives of data. Communication wraps around. That means when I'm trying to shift my data, communication is done between the processes, and repeat the same for each column. Now let's take an example starting with the matrix A. Here this we leave it untouched, we don't do anything. So A00, A01 and A02 remains as it is. When we come to A10, you will observe here that in this I shift one block to the next block. That is, A12 will be shifted at the position of A11, A11 will be shifted at A10, and if we can have an imaginary line which will make that A10 will like this shift to this particular place. So this is what we get over here. A11 comes to the first place, A12 and A10. But when we come to the last row, here what happens? It is a jump which happens from the last to the first. That is, the number which is at the position 2 will be shifted at the position 2 of 0. So 2 2 comes here, 2 0 over here, and 2 1 over here. So it is 2 blocks which will be shifted, and the rotation happens like this. Now what happens next is, in the first case we jump 2 in the last row, but when we have this matrix over here which has come from the previous matrix, we again shift one matrix size. So 1 1 will move from here to the last, 1 2 at the position first, and 1 0 at the middle of my matrix. So this is how this row looks like. And A22, A20 and A21, which was in the previous iteration, was moving 2 blocks ahead, now will move 1 block ahead, as 2 1 will move here, 2 0 will move here, and 2 2 will move to the end of my block. So this is my final iteration that I will get. So I've got my final matrix of A. Now let's start with B. Similarly, we'll do it with B. This column remains as it is. There won't be any change over here. Now we'll start with moving B. So B, 2 of 1 will move to the position 1 1, 1 1 will move to the position 1 0, and 1 0 will be rotated and it will move to the position of 2 1. And this is how this will be moved. 2 1 will move here, 1 1 will move here, and 0 1 will come here. Now here again it is a jump of 2, so B2 will move to the first location, 1 2 will move here, and this will move to the middle as in the rotation matrix. So this is what we get after the first queuing of the column. Now what happens next? Now it will be shift of 1 each. So 0 1 will move to 2 1, 2 1 will move to 1 1, and again there will be a rotation. So this is after the rotation. I've got the value over here, and this rotation what I did, I've got a value over here, and 1 2 to 0 2, 0 2 to 2 2, and when I rotate it like this, I get the final matrix over here. So after skewing of matrix and moving the rows and columns, we get the final matrix of A and B like this. Now we have to do the Cannon multiplication. So if we have to do the multiplication of C of 1 2, which is this particular part, so it will be the actual values that come after the multiplication from this row, and it will be multiplication of this column. So whatever values are there in this row and column will be multiplied for the Cannon multiplication. Thank you.